Hello and welcome to the Homeland Defense and Security Information Analysis Center webinar covering the National Renewable Energy Lab's Consolidated Utility-Based Energy Hybrid Energy System. My name is Steve Redifer and I'm the Director of the HDIAC, and we have the privilege of hosting Mr. Greg Martin for today's presentation. I'd like to thank our sponsor, the Defense Technical Information Center. The DTIC-IAC mission is to collect, synthesize, produce, and disseminate scientific and technical information to the DoD and federal government users. And this webinar is made possible through DTIC sponsorship. I'd also like to thank all of you for taking time out to join us today during these challenging times. So a few housekeeping notes as we kick off. Please note that all the lines have been muted for attendees. If you have questions during the webinar, they can be submitted using the attendee chat box that you see on the left-hand side of your screen. We'll work to save the last 10 minutes or so of the presentation to go over those questions and discuss them. If we run out of time, we'll make note of all the remaining questions and post responses at the conclusion of the brief. Please also note that this webinar is being recorded, and we will provide links for the recording on our website, www.hdIAC.org, for later download as soon as they're approved. With that, it is my pleasure to introduce you to today's presenter, Mr. Greg Martin. Greg is the Engineering Group Manager at the Energy Systems Integration Facility, National Renewable Energy Laboratory. He has been at NREL working in microgrids, hydrogen systems, and grid technology integration for the last 12 years. Greg was part of a small team that developed and built the CUBE, Consolidated Utility-Based Energy Prototype Hybrid Energy System, which is our topic for the day. Greg also had a foundational role in the design and specification for the Energy Systems Integration Facility, and he continues to work to develop and operate the facility today. Greg received his Master of Science in Electrical Engineering from the University of Colorado Boulder and his Bachelor of Science in Electrical Engineering from the University of Wisconsin-Madison. So with that, the floor is yours, Greg. Thanks.
Okay, thank you for that very nice introduction. Just want to check to make sure the audio sounds okay. And with that, I will continue into this webinar. So the CUBE, Consolidated Utility-Based Energy. As Steve kind of mentioned in the introduction, this is a hybrid energy system that's intended for military use. And we have worked with several customers along the way to develop this exciting technology, and it's a kind of a fixture of demonstration of NREL's capability and our lab capabilities. And so I'm going to go through kind of the story of the CUBE today. So my presentation outline is to first lead with the kind of conclusion, I guess, with the overview of what the CUBE is right now. And from there, this whole thing is kind of a story, but I'm going to kind of take us through the progression of this program over the course of more than a decade, and talk about some of the high points along the way and the reasons behind how this design and prototype ended up the way they are. So that's going to involve technology, design, and then prototype, kind of the hardware question, as well as some testing. And if time permits, there's a couple of other notable Department of Defense pointed initiatives at NREL that might be of interest to this group. So first, I wanted to dedicate this presentation to a friend and colleague and co-worker, Mari Shirazi, who really was the driving force behind the technology for this entire system, and has undertaken the heavy lift for making this thing all work and pushing it through to the finish line. She's fantastic, she's dedicated, and I've learned a lot from her. She's now at the University of Fairbanks, Alaska, and working in the a similar energy sector on both private and Department of Defense kind of research and development work. I also wanted to call out Dr. Bill Kramer, who was the initiator of this project with U.S. Army MEP early on. He developed the relationship and the kind of initial ideas for this technology and pushed it through into a viable program. So Dr. provided vision and leadership and mentoring, and of course learned a lot from him as well. So going on to the CUBE overview. This is a recent fact sheet, and I'm sorry, this is a bit of an eye chart, but I just wanted to talk through it. This is available on the NREL.gov website if you have a need for it or want to kind of read the more detailed descriptions here. But basically, this is a hybrid energy system that is intended for a small, I guess, forward operating base type of scenario. And the intent here is to reduce diesel fuel use. So there's a photo of the CUBE here, kind of the lab version of the prototype. And there are some ideas for ways to use this that even go beyond forward operating base type scenarios, such as disaster relief, or even, private sector energy surety, or hybridization of traditional diesel fuel or other types of generators. So this is a 2-page fact sheet. Of course, we've got some application ideas here and some further information as well as contact information. So go to NREL.gov and you can search and find this by searching the publications database for CUBE. And I'll have that information later on in the presentation as well. So going to the project overview. So the initial thrust from the Army and why we partnered with them on this was the goal of reducing diesel fuel use in standard generators at forward operating bases. So of course, the tactical quiet generator or other types of diesel fuel generation used on typical forward operating bases are known and loved and used extensively for tactical and more kind of domestic type of operations. In order to reduce diesel fuel use, the idea was that we could use energy capture from the local environment wherever these things were deployed. So a deployable solution that was lightweight, reliable, and transportable is key here. So we were charged with designing, sizing, and developing a prototype and a demonstration of something that could do this. So the story, and by the CUBE story, I kind of mean the programmatic storyline of the overall view of this program. Starting in about 2007, this project got kicked off with Chris Bolton and PM MEP. And I forgot to mention one thing I wanted to mention at the end. Chris Bolton, who PM MEP is now called E2S2, was the brain behind the name of this technology, the CUBE. So he named it Consolidated Utility Base Energy. So I wanted to call him out for that, as well as fantastic stewardship of this program for many, many years and leadership. So that started in about 2007, and we did analysis and gathered data and made sure we understood all the customer needs and the application of what kind of technology we could potentially design and build here. And we got some continuation in 2009, which kind of marked the start of let's build a prototype based on the analysis we've done, and we've determined what size and what features this thing should have. So for the next couple of years, the prototype was, the detailed design was done, the equipment was ordered and assembled, and there was some initial performance testing done. About 2012, so this initial development was done at NREL's National Wind Technology Center, which is about 22 miles north of the main campus near Boulder, Colorado. We moved the CUBE from there to the NREL's newest facility at the time, called the Energy Systems Integration Facility. And this is an integration facility, obviously, it was just right for being able to put this cube inside in a large high bay lab, connect up some diesel generators and the solar battery, PV, and all the other assets needed to run comprehensive testing and demonstration with it. So we started a solid program of performance testing to validate the predicted fuel savings and other performance parameters through a partnership with Wiley Labs and Army Rapid Equipping Force, about 2013. 2014, that performance test was completed and a report was released, and that's also available on NREL.gov. From there, there was some minor refinements made and polished the thing off, and we also did some technology upgrades as part of the Wiley Army Ref support, which included a DC transformer, 4-leg inverter, and flex grid input. So now we can kind of chain these things together to microgrid them. We implemented some weight reduction technology for the DC transformer, and also a load balancing capability. And then finally, we've most recently worked with HALA. Really, that was a kind of overall microgrids control project that used the kind of a node on the system to demonstrate the feasibility and performance of a microgrid control system. And also of note, in 2018, NREL received a licensure for some of the CUBE technology and approach that was a portion of this technology that was available for public licensing. So there's other portions that are just available for military licensing, so that kind of gets complicated, but we did get some private sector interest in developing this. Okay, so early analysis, nothing fantastic here, but basically we worked with our customer and figured out requirements and data, including like load profiles, what the situation on the ground looked like for forward operating bases that this could be potentially applied to, and use that to come up with architectures that would allow us to integrate solar and PV, which were the two kind of energy storage plus an energy generation source that seemed at the time to be the most tactically feasible. And that was kind of determined in conjunction with our Army customer. From there, we used a tool called Homer. Boy, I'm sorry, I don't remember exactly what that acronym stands for, but that was a tool developed at NREL for kind of microgrid or hybrid power system, economic analysis and technical analysis. And I'll show a little bit more about that. Now Homer is a private company, so I think people have to pay to use it. That led to a size, weight, fuel trade study that allowed us to kind of down select on what the different ideas were for what to pack into a box, and what could be built in the field. A conceptual tactical platform emerged, and then that fed back to the customer, and we went through this actual loop a few times, and you'll see that through this kind of initial story I'm presenting here. So some of the key design requirements and limitations that we set out with were that we needed to integrate with the tactical quiet generator, TQG, with no design modification. And I'll say that Mari and myself were interested in discussing other options, because this is definitely a big challenge. It's a isochronous generating source, meaning it is always the voltage and frequency master, and it does not parallel with other stuff easily, except it will parallel with other TQGs because it's been designed to do that. So we wanted to see a variable frequency generator, which would have allowed us a lot more flexibility in integrating this into a hybrid power system. But that was a limitation that we were able to accommodate. Of course, transportable for forward operating base, resilient for mil-spec environment, field deployable, and approximately 60 kilowatts, which was something we would kind of dance around to see if there are different sizings that made sense, but it emerged to be about 60 kilowatts for forward operating base. So first up, we went through tactical quiet generator, diesel fuel efficiency curves. So we determined what using real data from our customer, from TQGs operating in the field, we determined fuel curves for how much power we got out, how much fuel we burned for X amount of power, and we use this in our modeling. So there's 4 different sizes of TQGs, and we, for this purposes of this cube, we focused on the 30 kilowatt, but we also had the opportunity to plug in, or the ability to plug in, both 15, 60, or even 10 if we needed to the cube. So Homer, this is the kind of 2009 version of the user interface for Homer, where basically you specify an electrical architecture, and each one of these items are data-filled items or instantiations of different equipment that have different parameters and parametrics that allows this tool to analyze the both power flow, kind of high-level flow, as well as the kind of optimization parameter that you're looking at. In this case, we used diesel fuel cost, and that became a challenge because diesel fuel cost in this scenario could have a very wide range of values. And you know, those diesel fuel costs can go really high for tactical applications. After Homer, we figured out some optimal configurations for fuel reduction, and we applied some basic tactical conceptual platform to that. So we selected a generator size. Homer helped us select the generator size. We used a load profile. We used Homer to help us size a battery, as well as a solar panel. And then in this spreadsheet, we did research to determine what the weight and size of these battery and solar components would be. And then we made a spreadsheet, kind of visual analysis tool to just kind of eyeball here, in this case, what would be an optimal solution for this particular load profile. So the fuel burn, all of these fuel burn in gallons, weight in pounds, and footprint in square feet were on the same axis. So you can kind of see the lowest blue bar is good because that's the least fuel burn. The lowest red bar is the lightest solution, and the lowest green bar is the smallest footprint solution. So looking at these and, you know, going through this with our customer, we looked at this kind of scenario for the system. That led to a concept that we kind of had some CAD work done to develop what it might look like, and, you know, did iterations with our customer on ideas for this. And this idea is a 20-foot ISO container that has diesel generators in it. It's got PV, so the diesel generators are inside of this box. It's got PV, rolls of PV array, and it's got some batteries inside of it, as well as all the power electronics to handle energy flow. Little trade study on the size of solar in the field. So we looked at some ideas for rollable, flexible, deployable solar panels. And this was, again, a snapshot in time around 2010, where, you know, of course, solar technology has gone leaps and bounds since then as far as energy efficiency and effective power per square foot. But here's what we were looking at in 2010, just for general sizes and weights and footprints. This led to, you know, conversations with the customer led to a thought of, well, what if we did something smaller and kept the TQG outside of the overall box? And here's a concept to have batteries and PV in a trailer-like mounted solution that we could then pull up next to, say, a TQG and hook it up, and then have some kind of interface designed. This kind of thought process really led to what the cube ended up being, and I'll get into that. So here, this was kind of the next closest to what the cube actually looks like without the PV and the battery inside. So obviously all the power electronics take some space and footprint. We actually developed a prototype of a deployable roll-up flexible PV array to provide to the Army as an idea or a feasibility concept for what they might be able to develop for use in the field. This was a partnership with a local company that we struck up. The company was called CTD. They did a lot of space applications, and they had some interesting technology composites that basically had these rollable and deployable, I guess unrollable and snap into place type frames. Think of those old snap bracelets from the 90s. Basically, you kind of start the end and the thing just wants to roll back up, and then when you unroll it, you snap the end into place and it stays rigid like that. So this is a really lightweight solution and is able to be stowed and unrolled multiple times. Here's just another graphic photograph of somebody actually doing this. So it rolls up to a flat kind of plane, and you got a couple little wires coming off of it, and you hook it into something. So I wanted to play a movie at this point. This is kind of a more developed conceptual idea of what a forward operating base integrated power system might be. And hopefully, it looks like it's coming up. Hopefully everybody can see it comes through well. So I don't have a whole lot to say except, and that's kind of the point of this movie, is it kind of speaks for itself. But the idea is deployable using kind of more standard military equipment, and an integrated solution here includes a diesel generator on the inside of this box, a smaller one. So that one was a 10 kilowatt TQG. You can also see batteries inside of this box that are integrated with the system. There's the diesel generator, kind of the standard part that's integrated into the box. And then here's just a conceptual idea without showing the roll-up concept of what a more efficient, so the glass type solar is a lot more efficient. So we suggested that be an option to roll up into a box. And here is the power electronics and system controls end of the system that manages all the dispatch and power conversions needed, and then finally a user interface. The wind turbine was an early concept. We kind of learned that in some situations, a wind turbine is not ideal in a deployable scenario. So we kind of focused away from the wind turbine as part of this system. But I will say that an AC output of a wind turbine would be compatible with being able to plug into the cube as it is today. And that's kind of part of this overall flexible design and modular compatibility. So after all that, we settled with the Army PM MAP or E2S2 on a concept where we should keep all the peripherals outside of this conversion box, I guess, which is the cube, so that we can always use whatever is the best technology at the time to plug into the thing. So as solar increases in efficiency, or maybe other creative people come up with better solutions for deployable solar, that can just be plugged into this and not integrated into the design of the box. TQGs, if you have the TQG outside the box, of course you have the option of not using the cube if you just have a specific scenario need where you want to quickly throw a TQG and go, and you can choose to add the cube later. Again, batteries, same situation as solar. The technology was advancing quickly enough that weights and footprints were coming down, and efficiency was going up, and safety was going up. So we wanted to keep those as not part of the integrated design of the system. And then, of course, you need to connect to the real need to cube is to connect to loads and serve these loads to do a tactical mission. So that's the load connection shown there. So this is kind of the way we went when we went down the path of the prototype. And it's intended to be able to plug into lots of different sizes and actually voltages of solar arrays at DC, lots of different energy sizes and voltages of batteries. and then multiple different AC sources. And this, we showed TQG, but this could really be almost any AC source that was 50 or 60 hertz, and either 208 or 406 volts. So from there, we did some, design work to try to lay out what this cube converter interface box would look like. Internal cooling, big magnetics, those are those electrical components inside, some power electronics, transformer, and the controllers. So I'm sorry, this might not be extremely legible, but this is available in the report if you decide to go download the report from NREL.gov. But we approached this with two versions so that we could kind of do demonstrations and energy savings concept definition with a V1, and then integrate the full technology suite of the lightweight technologies in V2. So the main differences are V1 is, I guess, simpler than V2 because it's got a traditional 60 hertz line transformer in there to provide the load balancing and galvanic isolation from the loads. And that's not a weight effective solution. Those things are really heavy and big. But basically, to overview this V1 architecture, PV array inputs plugged into 4 max power point trackers on board the cube. So those handle converting the DC to DC into the system DC bus voltage, as well as a battery that you can plug in. And that has a battery charger discharger inside the cube also that interfaces and is controlled by the overall cube control architecture system. In V2, the main things that were added were a high frequency transformer. So instead of the traditional 60 hertz big heavy transformer, we convert this DC to a high frequency, allows your magnetics to get a lot lower, a lot smaller and lighter, but also provides the galvanic isolation needed to be able to do a 4-leg inverter and isolate the load. So this is a 4-leg inverter implementing load balancing. And also we added in V2 a microgrid, another AC interface port, basically a power port and another inverter inside the same cube box that allows you to plug in like a host grid, a utility grid, or this would be where you would plug in another cube that sits next to it if you wanted to go from 60 kilowatts overall load to 120 kilowatts. So some differentiating key design features. I've almost never seen a technology be able to do what this technology does in the kind of inverter synchronization world. Basically, this thing takes the TQG output and connects it directly to the load port. So that port is preserved. It's a hard connection through the cube to the load. However, the cube uses a really advanced inverter control technology and implementation that is linked with the contactor status of the TQG to seamlessly be able to parallel with that TQG output or instantaneously pick up the voltage if that TQG went down for any reason, even unplanned. And that's pretty hard to do in the inverter world. Mari was able to design and build this and demonstrate that it's a viable technology and it performs very well. So also we have the feature of load balancing implemented by a 4-leg inverter, and then a lightweight electronics solution overall here that's kind of marked by this dual active full bridge with a high frequency liquid cooled transformer. So here is the detailed power electronics 3-line for the key power path electronic architecture or electrical architecture, and a photo underneath the dual active full bridge high frequency transformer. So this is also in the report if people are interested in the electrical architecture, but this is kind of standard inverter topologies. And a key takeaway here is we're using the same power electronics brick for every function even if it's DC to DC, we use the same brick, but we only hook into 2 of those switches. For the battery charger, we might hook into these 2, another 2 switches on the same brick. So we used it flexibly to optimize utilization of these liquid-cooled power electronics, and it allowed us to, pack as much punch into this box as we possibly could. There's a robust protection, both for overvoltage, over current protection, as well as lightning arrest and things like that. Not going to go into that in much detail. This was needed for the reliability and safety. Overall control and signal architecture. Happy to discuss this more if there's time at the end, but basically we have these compact RIO, National Instruments compact RIO systems that are both a real-time kind of Windows-based or an operating systems-based microprocessor system coupled with an FPGA, field programmable gate array, that provides all the inverter control, and then the real-time head can do the kind of handling and communications across these things. And one of them is reserved for the master control, which provides the user interface and kind of coordinates on a high level what everybody else is doing. So in order to implement max functionality out of this cube, we had, like I showed, a tactical quiet generator plugged in, solar arrays plugged in, battery plugged in, and the load. And so there's lots of different mode transitions and different modes that you might want to operate this in. So as an example, one thing that was interesting for us and the Army customer was silent operations. So this would be pretty silent compared to a diesel generator. You would have that, inverter whine, but it's pretty low decibels, and it can be very well abated by shielding and insulating the box. So this is pretty involved to describe what this chart shows. It's who's controlling what AC or DC bus in what mode. But the left-hand list is the takeaway, that there's all these different operating modes and transitions that need to be implemented very intricately in order to make sure that the load is always met. So the CUBE prototype, as I mentioned, the controller systems, so both inverter control as well as kind of overall supervisory control and user interface were all programmed in the compact RIO platform, which provides a lot of different options for signal I/O, and it's got a FPGA backplane and a pretty powerful real-time processor head. The other opportunity with this compact RIO was that this brick in the center kind of gives you a development capability for prototyping to be able to change out cards and have high signal counts and get your application running and demonstrated. Once you've kind of stabilized all the configurations, you can move this to a single board, which saves time and is easier to cool. Saves space and is easier to cool, and is kind of more of a hardened platform that has less wires and things. I mentioned the power electronics brick. So the units that we used in this cube were the Semicron SCA KAI modules. These are hardened kind of vehicle power electronics bricks. They are rated at 200-ish kilowatts max power throughput. You've got AC and DC terminals, and then all the switches, and there are protections on the inside, and also this thing is liquid cooled. So this is pretty resilient, and it's hermetically sealed. It's reliable and rugged. So one of these bricks gives you a 6-pack of switches with a capacitor on the DC side. So some key prototype features. So to meet the environmental needs of the overall solution, we did liquid cooling, and this also allowed us to reduce the space needed volume needed for this prototype. But we liquid cool the power electronics, we liquid cool the magnetics using a cold plate. And then we have an internal air cooler. It's basically a air to liquid heat exchanger. And we also have liquid cooling to the high frequency transformer. So the major heat generating components, the overall internal air of this thing, are all dumped to a liquid cool system that's outside the unit, sits on top. It's outside the main unit, sits on top of the cube. And the main power electronics and controller components, so that can be sealed off from the environment. So that liquid cooling was a key design feature. When we spec'd and ordered parts, we got mil-spec as much as we could. When there wasn't mil-spec available for what we needed, we got the widest possible environmental resilient ranges of these equipment. I think we were able to get everything spec'd in this prototype down to minus 40 degrees C rated. And I'm not sure on the top end exactly. I think it was somewhere around, I want to say 40 degrees C or 50 degrees C max. There's the ability to program an intelligent dispatch algorithm on that real-time main supervisory controller, adjustable for the mission if needed, but we also provided a kind of default dispatch algorithm to save diesel fuel. So this is an open source design, so to speak, for the U.S. Army. It was sponsored by and guided by the U.S. Army, and so there are some IP embedded within this that's basically another national labs IP, which allows flexibility in working together across parts of the government to be able to eventually do a cost-effective licensing and product run and have control over the design and what the costs might be. So that was a key thing for our sponsor, to make sure to keep it open source, make sure we can reprogram it, and that there's not just one company or entity that could potentially come in and program this thing. It's modular, so it's intended to be able to be configurable by the user, configurable by the Army, and the Army ultimately controls the overall architecture and implementation of this system. So here's a photo of the original prototype. And this prototype sits on an actual tactical quiet generator skid. The skid skid we used was a 15 kilowatt tactical quiet generator skid. Gives you an idea of the kind of footprint. It's about 3 foot by maybe 5.5 feet. And it's roughly 4 foot tall without the coolers on top. And I'll show you another photo with the coolers. But front panel here is the circuit breaker for all of the inputs, and then these mil-spec connectors to connect in standard interfaces to tactical quiet generators, which are 2 of those big round ones on the right-hand side. One of those is the load connector. Those connectors are rated, they're 4-aught cables, so they're rated closer to 1 to 200, depending on your amps, depending on your environment. And then those smaller black-capped connectors next to them are 2 battery inputs and 4 PV inputs. So those are DC mil-spec connectors that could take the range of battery and PV, both voltage and power inputs that may be configured for deployment of the system. It's hard to see. There's 2 connectors underneath the kind of middle battery connectors there that are a little hidden, but those are 2 signal interface cables that go to the TQGs. So we've installed remote start kits on the TQGs that gives us some feedback on the status and alarming and contactor status of that TQG. So we need the Cube to have a kind of awareness of the status of that thing. So we also connect a couple of signal cables there. So that's really the main external interfaces to this system. In the back, there's a couple of 12-volt batteries to keep to ride through, to keep everything, all the brains alive forever whenever it's in use. And these get charged by the DC bus. There's a little converter to charge these batteries and keep them topped off. Through the center, it's kind of hard to see. There's the power electronics and the high frequency in this case, the line frequency power. In the front of this, kind of where all the yellow wires are on the bottom of the cube, those are the magnetics. So we got some kind of particularly made inductors that are required for the inverter output smoothing, and these are sitting on an aluminum cold plate that's tied into the liquid cooled system. Here's a view of the final prototype and everything hooked up to it. On top now you see a aluminum box that's kind of shielding a couple of liquid to air heat exchangers. So those are kind of just plugged into fittings on the top of the unit, and they bring the liquid loop out to these heat exchangers, and that's how we dissipate the heat. And those things ramp up and down based on what the temperature of the water is, so they don't run if they don't need to increase efficiency, and they dump the heat out of all the components and the air out of this box. I kind of already did this walk around, but some couple more views of this thing. Here's a view at the bottom right is a view of the back. You can see the batteries, and there's a battery charger there. You can liquid to air coolers in more detail. These are things that they use in long haul truck, like big diesel freight trucks, to augment cooling for hot environments. And so these things are pretty hardened, and they perform really well. They have variable speed capability for both the fan and the pump. A little bit on the diesel dispatch strategy. So like I mentioned, this is programmed to be able to dispatch all of the available resources, TQGs, solar, battery, in order to optimize and minimize diesel fuel consumption. So to do that, there's a couple of key parts of this, and there's always opportunities for add-ons to this dispatch strategy. But basically, you want to make sure that you've got some spinning reserve online. And in a case where you have a installation where there is no cube, you need to have, even if you don't need it, you need to have one backup generator kind of always running. And that results in oftentimes folks running 2 TQGs when they only really need one. And the requirement is that if one goes down, the other one needs to be immediately available, so spinning reserve. In the case of the cube, since we have this novel synchronization and paralleling capability, you can count the battery or the cube source as the spinning reserve, but nothing's spinning. We're not consuming any power. So you get the benefit of that kind of spinning sitting there that also has other functions such as augmenting power. You can shave peaks so that you don't have to turn on that second diesel generator. If your load goes above, say, 60 or 30 kilowatt, you can pump out some battery power or solar to meet that load demand, but not have to turn on another diesel. So this is kind of a general slide overviewing the prototype and the testing and kind of the overall features of this. So I think I've covered most of this stuff already. We used Mari primarily in the lab, set up a fully featured high-speed data acquisition system. We put a whole bunch of current sensors and voltage sensors and signal readers inside of the cube to make sure we assessed all of the different operating parameters and performance inside the cube, while we plugged in and managed these assets around the cube. So if you look at this bottom photo, there's the big black box to the right. That is a lithium-ion battery. It's from a traction, it's kind of private sector traction application, hybrid city bus. Thing's 80 kilowatt hour and 450 volt DC. So that was plugged into the cube. And then I think off screen there are PV simulators that we have at the ESIF facility that can simulate and play back any kind of installation scenario for any size array, voltage and current that you want. So we plugged 4 of those in, and then we just control those separately, so we didn't have to rely on actual sunshine in order to run through these tests. So we got the TQGs you can see in the background here. They're inside and plumbed to a Carmon exhaust inside the laboratory. And so this system was run using the load profile that was received from Army Ref and E2S2 as a viable load profile that covers the bases for a forward operating base. And we ran it for a couple of 24-hour tests, and we recorded in an intricate way the diesel fuel use and consumption. So we had, in line with those TQGs, a Coriolis flow meter that gave us a highly accurate reading of how much fuel was consumed. So we ran the load profile. We ran, I think I have the load profile on the next page, and we ran the battery and allowed this system to dispatch the resources, the solar and the battery, in order to meet the load, and with the objective of reducing diesel fuel use. And then basically we ran the same scenario with no solar and no battery, basically just the TQGs plumbed through to the load and measured all the same parameters. So that gave us a kind of one-to-one comparison of how this cube performed. And I can come back to some of those waveforms if people have questions later. But this is kind of the key takeaways slide. So here's the load profile and the solar profile that we used. We used a full installation day, so this is not a cloudy day, kind of indicative of a maybe desert environment. And that's kind of, if you think about the time frame when we started conceiving of this, the desert environment was on a lot of people's minds. We also overlaid on this solar installation. Here's the load profile we used. So this was a combination of kind of galleys, other needs for forward operating bases, tactical loads, etc. So we aggregated that, and you can see that 2 30 kilowatt TQGs could meet this, but a lot of this could be met with one and battery. And how much fuel could we save if we optimize this system? So then this pink box here kind of sums that up to show in the test. So I'm showing the comparison of the test to modeling. I'll talk about modeling in a second. But basically, this fuel reduction line here, the diesel-only system used 67.8 gallons in this 24-hour test with this load profile. The cube used 46.6. So we reduced to do the same job. So we reduced the diesel fuel consumption for that day by 31%, saved 20 gallons roughly of fuel. The column here that is titled model is a indication of, we did a completely offline model of this system that we as closely as possible modeled all the components and decision making of the cube to predict what the cube would do in this particular scenario with this load profile. It used REOPT, which is another NREL modeling tool that's pretty well received in the community. And the model predicted this extremely well. It was only, a tenth of a gallon off in its prediction of how the cube would actually perform in the field, and then we validated that with this field performance. So the only difference the main difference in the model versus the test is the model was not as easily able to predict when the battery would be dispatched. And so I added this little statement at the bottom from the final report that was one of Mari's findings. There's a lot going into this, but basically, if you look at this 31% of fuel reduction and say, well, how did you get that 31% of fuel reduction? The answer is that it was achieved by using the battery to prevent starting another TQG. So 63% of the 31% savings was by having the battery there, being able to do some transient overloads, and also spinning to prevent starting the next TQG. And that's important not only in fuel burn, but also in maintenance and reliability of running these TQGs. The remainder of the 37% of the fuel savings was the direct result of PV power input to the system. And that's a result of the PV array size we selected for this particular deployment scenario. So that's kind of the wrap up of all this. I wanted to point people to some resources available that go into a lot more detail on these test reports, modeling reports, and fact sheets that I've brought up during this presentation. So if you go to NREL.gov, NREL.gov, under the research tab, there's NREL Publications Database. And so all you have to do is search CUBE in that database, and you'll get a list sorted mostly by date of the most recent CUBE information. And there's 4 or 5 reports up there, including a fact sheet. Lots of folks were critical and contributed to the overall CUBE program and to its success. I just wanted to make sure I indicated several of them, and this is not extensive, but wanted to call out some folks. Of course, Christopher Bolton, PM E2S2. And it looks like there's a typo up there. It was originally PM MEP, but he was kind of one of the visionaries along with Bill Kramer to start this whole thing off and carry it through to the prototype phase. We have ongoing support and would like to thank Corey Goetz and John Spiller of the U.S. Army. And we also had good partnership from REF as well, Rapid Equipping Force, and Wiley Laboratories to kind of take this thing to the finish line and get to these final findings that we were able to get to. On the NREL side, we have a great team and lots of people contributed to this and made this successful. I already mentioned Dr. Bill Kramer and Dr. Mari Shirazi. Also, Dr. Blake Lundstrom was a key contributor for programming. And then a lot of folks helped us put this all together and get it working and running. So I've got, I think, 9 minutes left. Is there, I should pause here and ask maybe Steve if there's a format where we should go to Q&A.
Greg, we're good on time. Go ahead. I know you just got a couple more slides. Go ahead and run through those initiatives. It might spawn some more questions, and we'll get to the ones that we can.
Okay. So I want to draw a line in the sand here, I guess, just to say that was the end of the presentation on the CUBE. I'm happy to come back and do questions on that. And before we go to Q&A, I just wanted to run through a couple of other kind of highlights here with respect to NREL and our work in support of both installation and operational energy for the Department of Defense. So we've got a lot of experience, and we've done a lot of great projects in partnership with different branches of the Department of Defense. I'm not going to go into a lot of detail here, but you know, we do. I think the most key thing we do is the analysis and kind of installation techno-economic analysis and operational techno-economic analysis for the life cycle of some technology deployments and installations. We also currently are working a lot with electric vehicle integration and microgrids to support military operations. So we've got a lot of experience, and we're also growing our capabilities and portfolio of technologies that are interesting or needed in this sector. So to that end, here's a couple of projects that are currently pertinent, including, so I listed CUBE here because CUBE is ready for the next big thing at this point in time. I guess this is a past project. We did energy resource planning tool. So this was a combination of modeling and hardware testing in the Energy Systems Integration Facility laboratory to model a dispatch system that used a TQG with some other microgrid assets, and then also demonstrate the hardware running that exact scenario to validate the modeling. We're working right now on a modular expeditionary technology evaluation resource project that I have another, and that's focused on sensors and intelligence for microgrid dispatch, and also a energy storage in microgrids project under the ESTCP program. So we are moving forward with additional capabilities and expansion to support you know, tactical and military type technology. And I wanted to say, you know, that it's really important I feel really lucky that NREL has the ability to partner with the Department of Defense, because DoD is usually an early adopter of a lot of these technologies, and they help push the ball forward on the technologies overall. And so we really value that partnership, and we want to make sure that we're supporting fully wherever our expertise is needed. A new initiative at NREL is the Advanced Research of Integrated Energy Systems, ARES. So we're building out some more test area at the Flatirons campus now. This is the old National Wind Technology Center where the CUBE started, and now we're kind of going back there for some installations, rough concept shown here, installing a structure or two and providing access for potential vehicles with alternative fuels or electrical. And then we can integrate with solar, with wind, and other types of technologies, as well as grid. I want to make sure we have enough time for questions, so I'll kind of go real quick. This is a little bit more info on this meter project. Also, a program that is kind of umbrella over that, which is Nexus E, and this is kind of showing some of the reasoning behind doing this project. I'm happy to try to answer some more questions on this, but I'm not the expert. And if you want more info, we've got some contact information down here on this slide for Richard Bryce here at NREL. Thank you.
All right. Hey, Greg, thank you very much for putting that presentation together for us. It was very informative. I think one of the things that resonated the most, you talked about the 31% reduction that your 24-hour test run showed. So essentially, one of the objectives is extrapolating out. That means that fuel convoys running overland in hostile environments could be reduced by possibly as much as a third using this technology.
Yeah, sorry, I muted. Agreed, Steve, thank you. That's true. I think there's a lot of opportunity here to significantly reduce diesel fuel use. I would say that there's an extra need for fuel that's generated by having to deploy extra equipment, but I don't think that it's significant compared to what you would save by harvesting local energy and doing this type of intelligent dispatch of energy to right-size things for your load.
Right, and effectively taking convoys and soldiers, Marines, airmen, sailors off the roads.
Yeah.
So that kind of leads to the next question Robert Hayes asked. He says he missed to what extent that these could be daisy-chained together, and what are the opportunities for future scaling to meet, large power requirements, such as it not necessarily just at a FOB, but perhaps one of the big standing bases like in Baghdad or in Fallujah or something like that.
Yeah, absolutely. So daisy chaining is certainly something that is possible with these, and it was designed for. Going back into the presentation, I noted that we included as kind of the final phase of technology adjustments, a flexible grid interface. That flexible grid interface can be plugged into a host grid, like an electric utility. It can also be used to plug into another cube to chain these things together. And the approach to chaining them together would be to do a master-slave, so that we can identify one cube that's in charge of a whole string of cubes. I can't exactly sit here and tell you how many we could do. I think once you've gone beyond, say, 4 or 6 cubes in chained up, you probably want to start looking at kind of product for that application. And for that, I would say, and that's kind of what you're getting at with these larger installations, I would say that this architecture and this approach is definitely scalable for higher power levels. So I think the design and the foundation here is laid for being able to build something like this based on this design for much higher power installations. I would note that once you get to higher installations, you're not dealing with TQGs as much. You're going to be looking at a different diesel, maybe, or a different kind of AC, maybe, reciprocating source that may or may not be isochronous. So if you can get something that's droop or grid parallel, now your opportunities for other kind of more efficient or lower cost control integration are more. So to some extent, this can be scaled up depending on the limitations of what the other things you want to plug into it are.
Super, thanks, Craig. So that brings us right up to the hour. I'd like to thank everybody for joining us today. So as we mentioned at the beginning of today's webinar, we're going to work to get the webinar approved through the appropriate communications branches, and then once that's done, we'll place a recording of this presentation on our website, and it'll be available for download at www.hdIAC.org. If you're interested in learning more about the HDIAC or getting involved as a subject matter expert, a presenter like Greg has done today, or expanding your presence in our Homeland Defense community, please feel free to reach out directly using the contact information that we're going to post on the left-hand side of your screen. In addition to these monthly webinars, such as Greg gave today, the HDIAC also offers monthly podcasts that span the range of our 8 technical focus areas. We also put out a bi-weekly email digest that will be coming out later today with the latest scientific and technical news in the Homeland Defense community, as well as a technical inquiry service with up to 4 free hours of technical consulting. So if you have a question, go to our website, register, and ask away. If you're active in the Homeland Defense community and you're interested in joining our subject matter expert community, please reach out directly. Our subject matter experts contribute in a variety of ways, including presenting webinars, providing podcasts, and consulting as needed on the technical inquiries that we receive. Again, our contact information is included in the chat box. Be sure to join the HDIAC on May 21st for our next webinar, which will discuss forensic DNA analysis. Again, thank you for your time today. Best regards to all of you, and stay well.